Let's look at this simulation where we have pure water, just water itself. Look what happened to the pH. It is at 7. And notice how in water we have equal to, in terms of mole, the H3O plus equal to the number of moles of OH minus. So in a sense, the pH of 7 tell you that the values of H3O plus must equal to the values of OH minus in terms of mole. And that's an example of 7. Now let's look at a solution where we have an acidic solution. Okay, are you ready? So let's look at a strong acid solution. Look what happened to the pH. It has a pH of 2. Where let's look at the weak acid solution. Of course, the pH is now higher. And let's look at the base before we move on. Look at a strong base. Look at that, pH is really, really high. But if we look at a weak base, now it's going down. So let's go back to our pH scale. This one right here, it is very basic at 14. Where right here, at the very low number, would be very acidic, okay? So in a way, if we go down to a lower pH scale, it's becoming more acidic. If we go up this way, it's become more basic. Let's look at some example that we see in our daily life. First of all, stomach acid is right here. That's the same pH as your battery acid. And then we have lemon juice, we have vinegars, we have acid rain. Then past the neutral values of pure water, we have blood, is a little bit basic. Then we have soap right here, is at the pH of 10. Then we have bleach, which is a cleaning agent, has a pH of all the way between 12 and 13. So that is the pH scale. Now, we learned that the pH scale indicates how acidic or basic a solution. But a pH of a solution depends on two independent. They are not related to each other, okay? And these two independent factors, the first one is the degree of ionization based on its strength. Based on the strength of an acid, either strong or weak. And we just observe it, a weak acid would dissociate very little. Let's go back to our simulation right here. I have a weak acid right there. See how it's very little? This would be the acid right there. See how it has very little orange part, which is the H3O plus. Where if I turn to a strong acid, look at that. Do you see any more of this left in there? No, because it has completely dissociated. And the same thing with a strong base. Now let's look at a weak base first. This is the base right here. Notice how we still have some of the base left. We actually have a lot of the base left. But let me bring this into a strong base. Look what happened. We don't have any more of this left. It's all in colorful form. Notice how in strong base it's completely dissociated. Notice how strong base is completely dissociated in water. Now let's look at the graph, okay? So here, let's have water. Notice how in pure water we have H3O plus is equal to OH minus. So we have the pH of 7. But let's look at a weak acid. Notice how this is an acid right here. This is the same amount of water. Look at that. There are still of them. Look at that. There's a bunch of them left. And a small amount of them is dissolved into, in this case, H3O plus. But look what happened when I put a strong acid right there. All of the acid has been dissociated into H3O plus. Now let's look at the base. Notice how the weak base. There's still a bunch of weak base left. And some of them are being dissolved into the OH minus. But look what happened when I have a strong base. All the base has completely dissociated in form of OH minus. Look at the strong base. All of the base. Now let's look at strong base. It's completely dissociated in water to make that OH minus. So that's the difference between strong base and strong base or acid versus weak base or acid. Okay, a strong base or acid completely dissociated, where a weak base or acid partially, and I mean partially, a very small amount of it will dissociate in the solvent. In this case, it's water. So let's go back. As I mentioned before, strong acid and base dissociate completely, that's mean 100% in water. And then, but a weak base or acids, partially, okay, only small amounts of percentage, very small, dissociate in water. Now let's look at the second factor, the concentration of the solution. That means how many moles are in that specific volume of solution. So how is that important? Well, we just mentioned weak and strong acid, right? And this part is extremely important. That is because even if you have a weak acid, but if you have a lot of it, it will become as corrosive or as toxic as a strong acid that is diluted in a very large volumes of water. So be careful, okay? And we're going to look at that mathematically. Very important. So basically, I'm saying that if you have a high concentrated weak acid solution, it can be very corrosive. But if you have a very diluted or very low concentrated of a strong acid, it will still be very harmless. And again, just a review, calculate pH from a solution that are made from dissolving an acid, and calculate pOH for a solution made from dissolving a base. And we're going to look at that example in a few minutes right now. The first task is determine if a substance is an acid or base. Remember, an acid would produce an H+, where this one would be OH-. So these are the two things that we're looking for. Let's look at this one, HCl. Does it have any OH-? No, so it cannot be a base, but it has that H+ right there. How about KOH? It doesn't have an H+, but right there, we have that OH-. And notice how OH is a polyatomic ion, so it's always stay together. And that's the reason why you have OH- next to each other. Then we have HNO3. Do we have any OH-? No, we have the H+ right there. So this must be an acid right there. And this one must be a base and an acid right there. Let's look at the next one. H2SO4. Do we see OH? Of course, now we see that H. So this must be an acid right there. How about calcium hydroxide? Right away, you see how that OH right there. This must be a base. And lastly, we have C2H4O2. This does it have any OH together? No. So right away, we have to assume this must be an acid right there. And this is the acetic acid in vinegar.